the stage to Chris now.
Oh, Stephen, thank you. That was a very sweet intro. I definitely identify as someone who is all over the place. Yeah. Okay. So, hi everybody. Thank you for coming. I just realized while we were sitting here that this title slide is dated for a talk I'm giving tomorrow. So sorry about that. I don't even know what I would call this event. Yeah. So today I'm going to be talking to you guys about what I call coherent measurement. And in particular, the connection that coherent measurements have to continuous measurements. Okay, so I thought a great way to start off the talk. Oh, here, let me hit play so I can. Okay, I thought I would start off the talk by asking the following question: is the position on a sphere a quantum observable? So I think this is a simple question, and I think you guys will think it's simple too, but you have to pretend for a moment that you don't practice quantum theory. Okay, so if you pretend for a moment, I think the words position and sphere still mean something to you. But what I mean by quantum observable here is I'm imagining just white dots appearing 1, 2, 3, 4, 5, 6 in the shape of a sphere. Okay, so this is what I mean by position on a sphere being a quantum observable. So I think, yes, the position on a sphere is a quantum observable. However, you can quickly see that there's actually no such self-adjoint operator to assign to this kind of a observable or commuting set thereof. And the proof is pretty simple. The observation is that if you had such operators, their eigenvalues would give you a global coordinate system, and such a thing does not exist. Okay, so yeah. That would be a good way to start off, give you guys an idea of where I'm coming from. So I think it's fair to say, and somebody please tell me if you have been taught otherwise, but I think we're all taught to identify observables with self-adjoint operators from the beginning. So it's important to point out that self-adjoint operators can always be identified as observables, or you can always imagine them as such. But you shouldn't think that observables have to be self-adjoint operators. Okay, so I think we all accredit this program to von Neumann, and we call this the von Neumann measurement, right? So there's these notions of complete bases and orthogonality, and that all of these outcomes are associated with some operator or commuting set thereof. Of course, this is a very good way to imagine measurement. These are three examples that are particularly important. So I guess one of these is a monument of Stern and Gerlach. So there where they were diffracting or deflecting silver atoms in a uniform magnetic field, there the observable is the Pauli Z matrix. And here I've got the hydrogen spectrum. So there the observable is Hamiltonian at time t equals infinity minus the Hamiltonian time t equals minus infinity. That's a self-adjoint operator. And then here is also the Hitachi experiment, which I know Mike really likes. Where there, you've got two commuting observables. One you don't really care much about is the position in the vertical direction. The other is in the horizontal direction. Okay, so yeah, those are quantum observables that are very von Neumann. But another important example of a quantum observable is actually the standard coherent measurement. So I'm going to use the word standard coherent for the coherent measure states that you imagine in as applied to optics. But there, the outcomes of the standard coherent measurement form an overcomplete basis, right? This is a standard way of referring to it. And this kind of measurement is not von Neumann because the outcomes are not orthogonal to each other. But in a sense, these states are almost von Neumann because they still are eigenstates under a common operator. Okay. Indeed, the measurement I'm going to be talking the most about in the second part of this talk is the so-called spin-coherent measurement. So in this case, as I was pointing out to you guys earlier, this kind of measurement is not very von Neumann at all, okay? In the sense that, well, there's still, these kinds of states are not orthogonal to each other, but there isn't even a common operator to imagine them being eigenstates of, okay? Very different kind of measurement. Okay, so what I'm going to be showing you guys eventually is actually all three of these measurements have something in common. Yeah, and I find what they have in common to be deep. Yeah. All right, are there any questions at this point? These are going to be the three prime examples, and I'll keep talking about them over and over again from different angles. But
I guess I'll start it with a question. So normally we teach that if in a von Neumann case, if two operators commute, then they are simultaneously measurable.
Mm-hmm.
And will some analogy of that concept to carry on through here?
Sure, yeah, and then some. So I guess when I talk about von Neumann measurements, when I talk about common eigenstates, I am also including commuting sets thereof. Okay, so yeah, I don't mean to imply it has to be one operator, but I think mathematically, you know, if you have commuting operators, you can sort of put them together to make one operator. You can add them with just right linear combinations, sort of put it into this picture. Yeah, it's important to recognize them. I am imagining or commuting sets thereof. That's still von Neumann. Yeah. Okay. Yeah, that's a good question. Thank you. Is there any other questions or comments? No. Okay. Okay, let's see what I've got next. All right, so of course there is such a thing as generalized quantum measurement, and quantum information more than any community identifies with the existence of this field. Yeah, and in that case, what is the accomplishment of Krauss and those before him, including his teacher Ludwig, is this idea of the Krauss operator. So I was just talking to Carl, I think this morning, about what is in von Neumann's authoritative book on quantum theory, and how apparently there's an, I was hoping to get that book before I gave this talk, but it has yet to arrive. But apparently, according to Carl, there's an appendix that talks about indirect measurements. So it's not like von Neumann was completely oblivious of this. But what's important to note is that all you really have to be thinking about are non-unitary operators if you want to consider the most general kinds of measurements. And that's what the Krauss operator is all about. Yeah, so here I'm not expecting to talk about this stuff in detail. If anybody wants me to go over this, I can, but I will specialize to weak measurements and continuous measurements in a moment. So I'm just flashing this up here to sort of survey the kind of things one considers in generalized measurement theory. Oh, there's a delivery truck that might be von Neumann's book. Okay, so let's see, where was it? Oh, so I really like this quote from, so Wouters wrote the preface of this set of lectures. And in it, he says the premise of the work discussed here is that the foundation of quantum mechanics can be verbalized, and the present lectures are an attempt to communicate them. Something you're going to notice as the talk goes on is I have a very, I've already given this strong opinion that identifying observables with self-adjoint operators was kind of a mistake. And it's a mistake because it actually makes it hard for us to verbalize the theory, right? Yeah, the way we use the word observable is not how we would use it in a general sense. Yeah, and so there are other words we use in a very strict way that maybe we'd want to soften. So I'm very inspired by this preface. Never met Wouters or even seen him in action, but he wrote good papers. Yeah. Okay, are there any questions there? Okay.
Okay, sorry,
so,
Chris.
yeah,
just one question. I mean, I can't resist asking. I mean, in that generalized story, you can implement any POVM with a conventional self-adjoint measurement on the ancilla system. And so I
Right.
suppose that's how I've always made that sort of make sense in my head. And like, well, I mean, what I'm saying is there, you're definitely opposed to the idea of connecting observables to self-adjoint operators. And I suppose that means you're opposed to my saying, well, a POVM is basically just a self-adjoint operator measuring an ancilla system.
Oh, yeah, only because I haven't. So, I really want to show you guys how to do the spin coherent measurement. And I guess there's some angle at which I'm looking at all of this that just saying that doesn't really tell me how to. Thank you. Just saying that somehow doesn't tell me how to measure a POVM whose outcomes are in the shape of a sphere, right? Yeah. So is that a fair answer? Yeah. I mean, that's my ultimate goal, is I want to tell you guys about how to do this POVM whose outcomes are in the shape of the sphere. And
it seemed to me from your paper that one of the main reasons why you focus on this generalization was the group theoretical background, so that you can basically unify the whole, basically there seems to be a unifying attempt here based on the special role of coherent states in group theory. So maybe that is another reason to, look at self-adjoint operators as not being so suitable because they don't connect so easily to a classical phase space, for example.
yeah, I think I definitely agree with those things. So yes, I'm a lover of group theory. That is the most honest explanation of how I got into all of this, is just by loving group theory. Yeah. But I still think that you will find what I'm about to say. Yeah, you'll see. It's different from what the authorities on group theory and coherent states usually have to say. Yes, but indeed my enthusiasm is because of groups. Okay, so for the next few slides, I'm going to be digging into continuous measurement theory, how I would formalize it so that I can tell you guys a problem I want to think about. This isn't the beginning of me building up to it. This is me just trying to give you guys a context for why I'm digging in the weeds for the next few slides. So in this green box is just a schematic diagram of what I would call a continuous measurement. Okay, so these little yellow boxes are sets of observables that you're going to measure weekly. And the thing to appreciate is that you can simultaneously measure non-commuting observables weekly, right? So this set of observables can be very general. It just has to be finite. And so this DW is indicating outcomes of a weak measurement. Yeah, and so in this case, I'm going to only be considering non-adaptive continuous measurements, in which case all I'm imagining is doing weekly measuring these same observables over and over and over again, i.e. continuously. Of course, I'll get different outcomes every time I do the measurement, and that's why I get these little measurement records. Okay, so that's the schematic diagram. I hope that gives everybody an idea of what I mean by continuous measurement. But ultimately, the way to formalize this problem is to think of an object like in the blue box. So in the blue box, this is just a Krauss decomposition, but it's the Krauss decomp of the associated quantum operation. But the decomposition, of course, is natural to the way this measurement is actually being performed. So I say natural as in, a lot of people would call this an unraveling, but these measurement records, these continuous measurement records are actually happening as far as the way I'm coming at this problem. Okay. So the thing to observe is there's actually plenty of measurement records that would give the same Krauss operator. Okay. And so the thing I'm calling a fundamental theorem has to do with making a statement about what the relationship is between the set of observables you choose and this measure for your Krauss operators after doing this forever. Okay. Is there a relationship? Oh yes, there's many. And in particular, the places where I know how to make a relationship are places where you can enjoy groups. Yeah. So there's this is where I'm coming from. What I want is to be able to solve for the effective measure for Krauss operators. Given a continuous measurement, such a thing exists. To what extent can we know what it is? Okay. Are there any questions there? So now I'm going to start digging into the weeds, the kind of Krauss operators I'm thinking of, etc. All I was hoping you got from this slide is a schematic idea of what continuous measurement is, some appreciation about the quantum operation, but I'll talk a lot more about that too. And that there's this thing I'm calling the effective measure. Hello, hi.
I was just going to say you're making the you're mainly interested in the case where you imagine the measurement runs to infinity. I mean, I suppose that is not really important detail, but you're interested in something that you can think of as a completed measurement where whatever dynamics goes on, you run the thing to infinity, and we're learning about the initial state.
Yeah, that's the way I'm phrasing the problem. So the solutions I'll be able to give you guys in a moment actually know what the measure is for all time. But yeah, I think a nice place to start is, presumably if you run this continuous measurement long enough, it stops measuring, and things like that.
That raises another question. Are you imagining a single quantum system being observed in time, or you can thinking about an ensemble of such systems all being observed as well?
That's a good question. I'm very pleased to see that you use this word ensemble. So is your question, how am I interpreting Z of P or Z of rho?
Well, Andrew said that if you make this series of measurements, you can determine the state, the initial state. That's not true if you only have one system.
Sure. Yeah. So all of this is just to get one outcome. Yeah. So all of this is a lot of work just to get one outcome. But the idea is so waiting for infinitely long is not the best way to describe this problem. So the problems I'm going to be talking about, there's actually an exponential collapse. So the POVM turns into its limit quickly. And so you can do it over and over again. But there's still this idea of the limit of the POVM, right? And so, yeah, I'm certainly not implying that this, I'm not personally interested in POVMs that would take forever to finish. Yeah. It's great. Are there any other questions or comments?
Yeah, Carissa, I have a question.
Hi, Justin, hi.
Long time no see.
Hi.
You're implying continuous time here, which is problematic experimentally. Usually an experimental detector has some finite response time. And so in practice, what you're collecting is a discrete sequence of partially time integrated signals. Does that factor into your discussion here? Because often, for example, the Markovian limit with Wiener noise doesn't actually apply if your time bin's too small. So what sort of idealizations or assumptions are you implying here about this question?
Yeah, I'm definitely going to be assuming continuous measurements as infinitesimal time. In the paper, I have a little section on what the effect of finite time measurement is. And it's a little argument that just shows that the whole thing is robust. So if you have finite time problems, what I call anisotropies, and that'll make sense later. It doesn't ruin everything. It just gives you something a little different from what you wanted. And Yeah, so, but beyond just a few calculations that are analogous to the interaction picture, except for Krauss operators, I haven't, which are in the paper, I haven't thought further. Cool. Are there any other questions or comments?
Chris, I did promise that if I was going to interrupt, I'd ask if you minded. Do you,
Please.
I would just advise everybody who's listening to hold their horses. Nothing's going to be taken to T equal infinity. It's all going to be one system. And very quickly, the system state is going to disappear. We're not interested in the system state. We're interested in these Krauss operators. And that is what is distinctive about what we've done.
Okay. Yeah, I guess if I could comment on that, the reason I have states here is just because I see that a lot of people are more comfortable with thinking about measuring a state. But yeah, there's going to come a point where the state is going to fall out of everything I'm doing. Yeah, and that can be conceptually challenging. But I guess this thing I'm calling the effective measure, yeah, it has nothing to do with the state either. And that's, yeah, cool. Okay, so in that case, I guess I'll take the hint.
Just
yes,
another point of
yeah,
clarification or question. So just so I'm clear, you're not going to be writing down the Krauss operator for any particular measurement record, right? This is going to be...
Well, that function is well defined. So given a measurement record, there is a unique Krauss operator that. So I think of this as a function. That doesn't tell me whether anything made this record happen. So does that answer your question? I don't need the record to be realized to do the math that I'm doing.
So I read that last line as integrating over the measurement record, right? So this is the average
and you'll
action.
See, yeah. So Mohan, hold your horses. I'm going to start giving you some expressions for what d mu of a is in certain cases, right?
Oh,
so yeah, is that okay if I?
Horses held, yeah.
Okay, and yeah, cool. Okay. So let's see what we got next. So yeah, I really like that Mike said ensemble. So QOVMs, okay, quantum operation valued measures, are not as popular as POVMs. And POVMs in turn are not as popular as the Born rule itself. But QOVMs are very important to me. And you'll see why in a minute. So first of all, what I've just done here, now that I'm expressing my quantum operation as a quantum operation value measure, is I've taken out the state. Okay, so I'm using this O dot notation. So O dot just means put rho here. But otherwise, this is a perfectly well-defined linear operator. Okay, and to call this a quantum operation value measure, to me, is to stress that this dW is to be thought of as being sampled, okay? But what's really important is that the way it's being sampled, or it's the way it's being thought to be sampled, isn't real. Yeah, you don't have to do the measurement to do the math. Yeah, so I have different ways of saying this. So one, write this expression as independent of the state. Two, this is what I'm thinking of and why I was happy to hear Mike say ensemble, is when I look at this expression for a quantum operation, what I see is something that's formally identical to a partition function, okay? Where, the original partition function is, sum over microstates, Boltzmann weights. But in this case, we're summing over measurement records, and the object isn't a Boltzmann weight, but rather a back action operator, right? Okay, so is everybody comfortable with that? I'm calling this a back action operator. It is not, so each of these back actions are not quantum operations themselves. Nevertheless, they can happen. and you would normalize upon their realization. But otherwise, having this sort of sum over records, these operators, you have an object that can be formally treated just like a partition function, except there's all this non-abelianity or non-commutativity, of course. But I still find it very meaningful to think of when I say the record is, this is like our ensemble of back actions to be sampled. That means a lot to me. Okay. Yeah. Okay. So I guess the last thing I have to say here is it's not just a map, right? This measure aspect is taking very seriously these outcomes, but taking seriously these outcomes in a way that is perhaps subtle. Yeah. Okay. So that's just to say I'm going to be talking a lot about quantum operation valued measures. Okay. So this is just, yeah, that's what that is. Okay, so now what kind of measurement do I have in mind? So we're going to be talking about continuous measurements. So we'll just go through this nice and quick. The cross operator for a weak measurement is appreciated by many, including, I think, let's see. So Dan Steck and Kurt Jacobs wrote a review article on this. And yeah, Justin has written some stuff on these kinds of cross operators too. Yeah. So in this case, what I'm imagining is the meter state is a continuous variable state, as they call it, prepared in a Gaussian. The reason I'm imagining it prepared in a Gaussian is because, once we continue this measurement, because of the independence of the input states for the meters, the central limit theorem kicks in pretty quickly. So even if you used different kinds of wave functions, they would effectively act like Gaussian wave functions. Yeah, so I start off with these Gaussian cross operators. So the interaction is just to displace the meter state according to the observable with the system of interest. Okay. Okay, and so of course I'm going to rescale everything. So this sigma appears in the meter state and the interaction and the outcome, so that in the end I don't have to think about it. Yeah, and so so this is standard, something you can find in many places. This is me just plugging in. I guess I would call Q a Langevin noise, even though it's not noise, it's actually the signal. And this dW, I guess you would call a Wiener increment. So the first thing I'm going to do that's important to me is I'm actually going to think of this scalar part of the Gaussian cross operator as part of the measure. Okay. And so what I'm going to be calling the cross operator for a little while is just this operator part of the cross operator. Okay. So don't forget this. I'm going to have a lot of measures and dmu of dw's and lx of dw's, and they're always going to be this. I'll keep saying this, but that's an important element. Okay, so now what I'm going to call a simultaneous measurement is just the weak measurement of finitely many observables. Okay, so something to appreciate here is because the measurement is weak, the cross operators actually commute, even if the observables do not. Okay, so I have this funny subtitle. It says actually in parallel, contrary to the diagrams in series. Right, so even though I'm sort of writing this as if the state gets fed in and out, the order doesn't matter yet. Okay, but too many questions get raised if I sort of wrote an arrow that got split, and I'm not imagining cloning or anything. And you subject this to n measurements. Okay. So I'm going to write just a similar kind of schematic diagram with squiggles around the x to mean finitely many observables, and then vector sign over the measurement outcome, so finitely many outcomes. Okay. And similarly, the quantum operation valued measure is exactly what it has been. except with, yeah, multiple outcomes having Gaussian measure, and a cross operator that is simply a product of the individual outcomes. Okay, so nothing too sophisticated. I hope you guys appreciate that. You know, when I look at this stuff, the math like looks worse than what I'm saying. Right? At least that's how it feels. I look at the math too intensely, and like, oh my God. So I hope you guys are not intimidated by these expressions. Okay. Okay, so finally.
Can I ask a
hello.
question? When
Yeah,
you say
yeah.
the cross operators commute, is that to first order in DT? Is that like,
Right.
are you
right.
using the fact that, yeah, okay. Okay.
Yeah, to first order in, yeah, DT. Yeah.
Okay.
Yeah, so that's where it's important that these are weak measurements, and I am talking about continuous measurements. And there are effects when you don't do a perfectly continuous measurement. Okay, so finally, I'll define what I mean by a continuous measurement, which is a non-adaptive continuous measurement. So,
Chris, could I make one little comment?
yeah.
I think that was a key point that Mohan brought up, and I believe, and I just want to stress what your answer was and how it relates to other questions. For infinitesimal increments, you can put together as many non-commuting observables as you want, and the ordering of the Krauss operators won't matter. The minute you go to a finite time, which Chris is going to do, things are different. You no longer can, these things can no longer be said to commute. And so you are answering a real question as to what measurement you are making when you extend to a finite time. So for every finite time, one is answering a real question. What does this weak simultaneous measurement of a bunch of observables, what does it come to when you do it over a finite time? And that is true for every finite time from the smallest finite time out to infinity. And so the whole thing is going to be formulated with that time as arbitrary.
Okay, Mohan, were you, was that helpful? Cool.
Oh, and I can see you're about to see this, of course, on this slide. And of course, I should have known that because Chris and I looked at this talk this morning. So
What are we supposed to see? I can't remember what comes next.
well,
So.
now you can see piling up to a finite time.
Oh, I see. Yeah, so I guess this expression is, what did I call this? A QOVM path measure. I know I say measure here twice, but that's just one of the funny things about acronyms. Yeah, here it's the path ordering actually does matter, right? Because there's actually uncountably many terms here when you have DT truly infinitesimal and T truly finite. So yeah, you can get away with commuting countably many of these LXs, but not uncountably many. Yeah. Cool. All right. So now I'm going to state what I think are two fundamental problems. So here we are with this QOVM path measure. And the question is simply, what is it? Like, you know, it's not exactly comprehensible to look at it like this and say, oh yeah, I know what that's doing. So here is where I define this limit. Okay, this fact that, well, so this is an unraveling over measurement records, but there is somehow an effective quantum operation valued measure. Okay, has nothing to do with the state. It's, as Carl likes to say, piling up Krauss operators. And the question is just, how are those Krauss operators actually distributed? Okay, how are they distributed now that you've got this crazy sort of non-abelian thing? How do you pile up these Krauss operators? Okay, so the two fundamental problems I would say are, given us, you chose a set of observables to measure continuously. Well, what is this QOVM? What is d mu of L? Okay. That's a fundamental question to ask. And another question to ask is, well, if you had a d mu of L you wanted to do, such as a coherent state measurement, does there exist a set of x's you could measure continuously that would give you the P of EM you want to do, or the Q of EM? Okay. So these are what I'm calling the two fundamental problems. Maybe not the two, but they are two. Okay. Of non-adaptive continuous measurement. Okay. So of course, I'm not here to just create problems. All of this is to build up to, well, I have three solutions to this fundamental problem, both of these fundamental problems. One of them is one you guys already know. So of course, if I continuously measure commuting observables, then the limit is just a von Neumann measurement. Okay. All of the cross operators pile up to some eigenstate of simultaneous eigenstate of everything. So that's probably not surprising to anybody. What is also, I think, appreciated, but maybe not completely in a continuous measurement sense, is if you continuously measure the quadratures of Weil-Heisenberg algebra, that actually does implement the standard coherent measurement. Okay. And then this third one is, well, if you actually continuously measure the spin operators x, y, and z, that actually performs the spin coherent measurement. Okay. So I have these little check boxes on the side. So as I was saying earlier, I think box number 1 is well understood and nobody would be surprised. And I think even Tybron and others have literally done this, the analogous version of this problem for the von Neumann measurement, just to see that all of the measurement paths have this sort of concentrating property you'd expect them to have. I'm not sure anybody has thought of the standard coherent measurement exactly in this way. Certainly Arthurs and Kelly had something else in mind, what Carl and others like to call single shot measurements. Yeah, where you're not measuring for a finite amount of time. Yeah, and as for this third problem, well, yeah, that is what this paper recently published is about. Yeah, and this is going to be the subject of the rest of the talk, is how to actually see this. All right. Okay, so yeah, as I was saying to you guys, this is the subject of the recent publication. This problem was actually brought to my attention by these guys down here. This is Amir Kalev, Ivan Deutsch, Carlos Riofrio, and Azad Shojai. They were very interested in this problem, so they brought it to my attention. And we wrote a little paper in 2018 because we had enough to show that they just wanted to show you could do this spin coherent state POVM. But I wanted to do so much more to be confident that the result was correct. But we wrote a little letter in 2018 announcing this. They were perfectly happy with stochastic differential equations only. Yeah. But yeah, and so here's the yes, exactly, but what does the math look like? So there are sort of two other levels in which I wanted to do this program. I've already exposed you guys to sort of path integral way of thinking about this result. But I'm going to be spending the rest of the talk talking about diffusion equations. So yeah, solving it in these sort of three ways. So I'm not going to talk about stochastic differential equations. You could read this 2018 paper. You can also read one of the last sections in this recent publication. That's actually a bit better written or more carefully written. So I'm not going to talk about that. I already talked to you guys about path integrals a little bit. But I'm going to quickly convert things into diffusion equations. Yeah, so this became for me quite an invocation of ideas yeah, who come from these faces I've displayed. So yeah, I guess I'll read these off. Do you guys know all these people? So this is Sophus Lee, Bernard Riemann, Klein, Killing, Kolmogorov, Cartan, Wiener, Weil, Wheeler, Armand Borel, not the measure Borel, the group theory Borel, Ito, Feynman, Krauss, Helgeson, who's really into symmetric spaces, one of the biggest motivations behind Cartan's theory of differential geometry. And yeah, and Mike are here and Stephen are here. I hope that doesn't embarrass you guys too much. But this perspective I've always had about tomography comes from you guys. And that's been a really important part to me. I don't think I would have appreciated, I've been saying to my colleagues forever, like, don't people understand the QOVM is independent of the state? And this has been a big driving force. And for me, yeah, and I don't know. Yeah. So everything we're about to do is going to be math that explains exactly what this arrow is, which is that all the Krauss operators go to operators that look like this. They're basically projectors onto spin-coherent states, but the post-measurement state is actually not the same state as the outcome. So these are slightly different. I don't know what to call this kind of operator, a rank 1 spin-coherent operator or something like that. Actually, that's a good name for it. I should say that. Okay, so now I'm going to step into actually showing this. Oh, not just
Chris,
yet.
Chris,
Hi.
why is Wheeler's picture slightly bigger than everybody else's?
Oh, just because I didn't really have the energy to trim his face out. So yeah, there's just a lot of space around his head. Yeah.
Well, I endorse it.
Yeah, I mean, I'm a fan of Wheeler too. Are there any other questions or comments? Okay. So before we proceed, I thought it was important to actually quickly go over the history of coherent states and coherent state measurement. So let's do that real quick. So Schrodinger is credited for being the first to publish on what we call coherent states. And this was in 26. And I think it's fair to say that he would not have been thinking about that problem if he wasn't so close to Weil. At that time, right, both of them were chairs of their corresponding departments in Zurich. And they were so close that Schrodinger was happy that Weil was dating his wife. And yeah, so Weil in 28 wrote his authoritative text on applying group theory to quantum mechanics. So he almost surely thought deeply about coherent states. Yeah. Meanwhile, Wigner also thought quite a bit about coherent states, and Wigner also wrote an authoritative text on the application of group theory to quantum mechanics. But what's interesting to see is, there's what we call the Weil map. This idea that given a function, how would you assign, say, a density operator? It's called a Weil map. And Wigner also thought of a problem where, given a state, so he wasn't thinking in terms of density operators, he was thinking in terms of pure states, but hopefully this arrow is still clear. Given a state, there are these interesting functions you can think about, and we call this the Wigner transform. Moyle contributed to that whole conversation is making more obvious that what we call the Weil map and the Wigner transform are literal inverses of each other. And I believe this was surprising to people. Yeah, I think it's always easy to have the attitude from the beginning that quantum is somehow more, but at least in the case of these kinds of phase-space correspondences, no, the Weil's quantization program and Wigner's thoughts about turning operators into functions were inverses of each other. Yeah, so that was the first wave of coherent state appreciation, I'd say. Then there was a second wave. So in 1960, Clowder wrote an interesting paper. The point of his paper was to demonstrate that fermions actually have commuting C-number path integrals. which is really interesting. It was 55 when Grassmann numbers were introduced for fermion path integrals. And of course, they're much better if all you want to do is calculate correlation functions. But yeah, if you're trying to think about probabilities and things, well, I don't know what motivated Clowder to want a commuting CNUP path integral, but it's something you might want. And there, the point is, you can think of fermions as sphere-valued functions instead of complex-valued functions. As long as you can, as long as you think of fermions as sphere-valued functions, you can do the whole program. You have to have discontinuities in the sort of classical contributions to your correlation functions. And that can be offensive to some people. Clowder calls them unruly. Anyway, so, but he never calls these coherent states, of course. He just calls them over complete bases. And he plugs them into, the Feynman path integral expression for propagators, just like we all know, just using these over complete bases. His interests were fermions, but of course he mentions bosons and their over complete bases so that it's obvious the fair comparison to make. Yeah. So of course, soon after this, and I think a lot of you are aware of this, Glauber would proceed to spell out how to actually use, calculate, and think in terms of coherent states for quantum optical calculations. And Gilmore would step in about 10 years later and start spelling out how to think about these kinds of coherent states, like spin-coherent states. And his legacy calls these kind of coherent states atomic coherent states, I think because he was being complementary to Glauber's optical coherent states. But at the same time that Gilmore was spelling out how to apply these kind of coherent states to atomic systems, Perelomov was explaining how coherent states are an aspect of Lie group theory. Okay, and something to appreciate is these optical coherent states. They're associated with a Lie group that has a very different personality than the group associated with atomic systems like SU2. And this different personality has a name. It's called nilpotent versus semi-simple. Nilpotent means that in this case, all double commutators are 0. So everything sort of disappears as far as higher order commutators are concerned. Well, semi-simple means it doesn't matter how many times you commute, nothing goes away. Yeah, so very different personalities. Okay, but as far as coherent measurement is concerned, so Arthurs and Kelly, along with Glauber, had the guidance of the invention of radar and the laser. And so this paper came out soon after Glauber's work explaining the simultaneous measurement of the observables of the Weil-Heisenberg group. This was a surprise to a lot of people because if you recite the Heisenberg uncertainty relation, you probably will say things like you cannot simultaneously measure Q and P. So people had to think hard, but Arthurs and Kelly were forced to think hard about the simultaneous measurement of Q and P because engineers were insisting that they were doing that kind of measurement. Okay. So Dariano, there he is, in 2001, he understood or was convinced, and he was right, that there is some kind of analogous result as the Arthurs and Kelly result. Okay, that if you simultaneously measure these spin components, that should do the spin coherent measurement. But he wasn't able to show it beyond spin j equals a half. And it's because he was trying to produce the same result with Arthurs and Kelly's argument. But as I hope will become clear later, and it's part of the slide. So here, I won't talk about that just yet. You can't use the argument that Arthurs and Kelly give for the spin coherent measurement. Okay, so that is a quick review of the history of coherent states. Are there any questions or comments here? Okay. Okay, this slide, oh, I didn't animate this like I told myself to, sorry. The point of this slide is to just say, why should you think about coherent measurements? Well, I think about them because they're tomographically complete and complete in a way that is of minimal expense. Yeah, this is just to acknowledge that von Neumann measurements are not tomographically complete. So you have to think harder about what it means to understand completely a quantum state. So what I mean by minimal expense is what does it take to actually, so coherent measurements, the outcomes of a coherent measurement have a special name. They're called Q functions. But taking the Q function and actually making further predictions requires you to be able to invert this kind of operator. And it's the inversion of this operator, which I'm partially calling the expense. The other thing, the other expensive part is, well, what does it take to actually do the measurement? Yeah. Okay, so, okay, here's one more random fact that I think is just, I don't know how to say this is important, but I feel like I have to say it so that, yeah, I just have to say this. So spin coherent states and standard coherent states, they have a very different personality when it comes to how they behave on their copies. Okay, so when you take copies of standard coherent states, there actually exists a unitary. So if you work in optics, right, there are some beam splitters that put all these coherent states into the same mode. So in this case, you would say that, yeah, copies is really the same thing as rescaling H bar, okay? And this is something people do all the time. And it can make not very clear that when you're rescaling H bar, you could think about it as making more and more copies. But if you do the same thing for spin, well, you actually get something different. So when you take copies of, say, this spin half state, you get different objects. And so in representation theory, you would then say that there's only one inequivalent representation of the Weyl-Heisenberg group. Well, there's actually many inequivalent representations of the rotation group. And just this difference in their personality makes people handle the associated algebra very differently. So I thought I would say that off the bat. And I also say this to say that all of these kinds of resolutions of the identity, so for different J's, are things I am also calling spin coherent DOVMs. Okay. Okay. So just in case, you know, I motivated spin coherent states with what Clowder was thinking about. I'm not just thinking about qubits, okay, two-level systems, when I say spin coherent state DOVM. Okay, so I felt like I had to say that. So now, to explain to you guys this solution number 3. Okay, so the isotropic measurement is, as I think I've already said a few times, the measurement of the spin X, Y, and Z components simultaneously. And so we formally already described this problem. And the thing you should notice algebraically from the get-go is when you do a measurement like this, these quadratic terms no longer affect the evolution of the cross operators, right? And that's because this quadratic generator is what's called a quadratic Casimir operator. Yeah. And so in that case, what that means is that the multiplication of these cross operators become representation independent. What that means is it doesn't matter which J I consider, the cross operator you get at the end has its value independent. So you might as well multiply 2x2 matrices to get your final cross operator. So this is the function of the measurement record. So this is part of what makes a measurement like this cheap. is you don't have to multiply these arbitrarily large matrices. You're just multiplying 2 by 2, no matter how big the spin is. Okay. And so here, finally, I can introduce a more concrete version of what I've been calling the Krauss operator measure. So as you could see, these Krauss operators essentially don't explore the entire space of matrices. They only explore this submanifold, right? So I say these are representations of SL2C. What that means is that these Ks only live in a 6-dimensional space, right? It's basically a copy of SL2C, except it's weeble wobbling in SL2J plus 1. Yeah, so in that case, you can actually repartition the path integral expression for the superoperator using the Haar measure of that group that is homeomorphic to the place where the Krauss operators are actually going. So that Haar measure existing is very important, but what's equally important is that that Haar measure is accompanied by a delta function. And it's important that the existence of this delta function and the ability to use it in calculations comes hand in hand with the existence of the Haar measure. Okay, so this thing is defined as if I integrate against the Haar measure any function of g, it would evaluate it at g of dw. Okay, so so this is what Carl and I call the semi-simple unraveling. Okay, is this expression of the superoperator for a isotropic measurement as a sum over Krauss operators that are now enumerated by elements of this group SL2C. Okay, so again, the Krauss operators in this ensemble are distributed in the shape of a manifold homeomorphic to SL2C. Okay, yeah. Okay, so just to be super clear, I'll make sure. So if you're talking about a spin J representation, these Ks are 2J plus 1 by 2J plus 1 matrices. Yeah, the ensemble, the actual terms that contribute to the QOVM are all representations of a of 2 by 2 matrices. Yeah. Yeah, I don't know how to convey there's a shape to this, except, well, there'll be slides later. Okay, so thus I've defined the Krauss operator distribution. Mohan, when I told you to hold on, I was thinking if I could point at this, then I would be ready to handle whatever point you were trying to make. Yeah, and so I don't remember what point you were trying to make when I told you to hold on. I just really wanted to point at this while you said it. Yeah. So I don't know if you remember either, and want to try to say it again.
Yeah, so I think I was saying, when you said that what you care about is the Krauss operator, solving for the Krauss operators.
Their distribution.
The distribution. I interpreted that as you weren't going to write down a Krauss operator for any particular measure on record, but rather the Krauss operator that represents, or the map that represents the average effect on the pre-measurement state, when you average over all records. Is that right?
Yeah, I can't say I'm connecting with you. Yeah, in terms of, I think we're asking a question, what do I want? And yeah, so average, it's very awkward for me when you start talking about averages. Yeah, and would you call this your average? These G mu of DWs?
That's an average over just part of the measure, I think, right? I think that ZT, that operator ZT, that represents, I think, the average effect of doing this measurement on that on the system, right? And by average, I mean averaged over all the measurement records. So I'm not asking what is the effect that's consistent with any particular measurement record, but I do this experiment over and over again. I average out over all the measurement records, and this is the resulting map. Is that the right interpretation?
I think it is, but I was trying to emphasize earlier that it's actually the measure aspect of this expression, which is what all of this work is for. So it really is about repartitioning this expression. And I find that meaningful. So when you talk about averaging, I don't know how to, this is also a kind of averaging. But this is an averaging that is acknowledging that your Krauss operators do something that has a pattern to them. And yeah, so you have a different expression. Yeah, and these are the things I want, are the shape of these Krauss operators, how they're arranging themselves. Yeah.
Chris, perhaps this is a case where I could make a comment.
Please.
So if you look here in that green box, representation of SL2C, you will see a whole sequence of outcomes and their Krauss operators multiplying up to give G of dW. You could convert that G of dW into whatever representation you're in, but let's just leave it there for the present. The point is that G of dW is labeled by this long path of outcomes. However, at time t, which capital T, which is where this ends, you might want to know the effect of that Krauss operator on an initial state in terms of statistics, that is the PLVM, and in terms of the post-measurement state, which is just a unitary stuck on the square root of the PLVM. And that's all in there, but many different paths lead to the same ultimate Krauss operator. And so you could regard the actual outcome after time t as labeled by the Krauss operator itself. And all of the paths that lead to the same Krauss operator have the same effect. This is implicit in every formulation of quantum measurement theory, that the actual outcome is the Krauss operator itself. So all that Chris has done here is to agglomerate all the paths that lead to the same Krauss operator and try to calculate their density or weight relative to the Haar measure. So the density or weight is dt of g, and the Haar measure is d mu of g. So this will allow you to say, after time t, where does this measurement live in the space of Krauss operators, which here is, as Chris says, this six-dimensional submanifold of the space of all Krauss operators, a six-dimensional submanifold that is equivalent to, that is homeomorphic to SL2C. And what we're interested in is knowing. The whole point of what we're doing is when anybody can see what making an infinitesimal measurement of the three components of angular momentum is about. But if you agglomerate up to a finite time, well, you'd say, well, that's measuring the same thing strongly, but we want to know what that means. And all of the meaning of what that means is in this density dt of g relative to the Haar measure d mu of g. That's why Chris has introduced all this, and that's why that will now be the subject of interest. Now, backing up a little bit, another conventional way of dealing with this would be to put the dt of g into the k of g's by putting a square root on it and including it into k of g and k of g dagger. And that would be a conventional, cross operators aren't normalized in any particular way, and they contain probabilities. But here we have chosen to separate out this density precisely because we want to know where in this 6-dimensional manifold does this measurement end up. And so the point of this slide is to tell you the way to get at that is the dt of g, and what Chris is now going to tell you is what happens to that dt of g. So we can answer the question, where does this measurement end up? Sorry, Chris. I was
such passion. Yes.
I was off on one of my rants.
That helps. Thank you.
Oh, good.
Sorry, Chris, can I just ask a question? I was
Please,
annoying
please.
previously about the finite time case, and I want to make sure I'm not sure if I understand these formula here perfectly. So in the first 2 examples you mentioned, I mean, if I was measuring, if the Krauss operator is all commuted, or if I was doing Arthur-Kelly type measurements, then what I would expect the POVM to look like at finite time is basically a smeared out. It would be like a Gaussian probability distribution over projectors on the coherent state. And I suppose I'm staring at this and I don't see that. So what I would expect is if I do the measurement for a shorter time, I will get a measurement outcome, but it will correspond to some Gaussian distribution over coherent state projectors that gets broader the shorter I measure the time I measure for. Is it? Can you just point to where that is in these formulae, just to help me orient myself?
Yeah, let's see. So so for every k, you can think of k dagger k, and you can think of the q function of k dagger k. Right. And you could also think of kk dagger, and that has a q function. And those q functions are spin coherent state expectation values. And if I were to sample g from the Haar measure, weighted according to these dt of g's, then, well, I guess for each sample, you would get a q function. And for small amounts of time, those q functions cover mostly the sphere, right? And indeed, as you're saying, those q functions are all going to tighten up to the spin coherent outcome. Yeah, quickly. So is that answering your question?
So it's in. So yeah. So you're saying that the. I mean, maybe inside this dt of g is that fact that the measure is tightening up.
The measure over the 2 sphere of every q function.
Q function, yeah.
Right. Yeah. So we're gonna talk about how to visualize SL2C in a little bit. Okay. And tight functions are going to be things that are out on the boundary of this space. Yeah. So yeah. So there's 2 spaces to think about. One of them is the phase space, which is the sphere, and the geometry of that is related to this geometry of SL2C. But the distribution you were thinking about on the sphere is 1G.
Oh, yeah, okay. So it's actually, okay, actually that really helps. So the point is, because this G is SL2C, so yeah, I should not, it could be inside a sphere or, yeah, okay, thanks. I think that really helps, yeah. I'm thinking in the wrong space.
Okay, but to each G, there is a shape on the sphere.
And Chris, this is a case where you need to get on to the Cartan decompositions, because then Andrew will see what the shapes are that you're talking about and what the dt of g is supposed to be telling us.
All right, sounds good. So
you should put him off and tell him come back after you talked about the Cartan decomposition.
Okay, Andrew, are you ready? We're about to step in to SL2C. Yeah. Okay, so as I was telling you guys, so now the name of the game is what is DT of G? I hope you guys don't mind. I am now sort of like a typical quantum physicist. I think this is Wigner's fault, this trend. But I'm going to be completely ambiguous about what the group element is and what the representation is, right? So I used to say K of G, now I'm just going to say K, right? But I'm still talking about things that are in the shape of SL2C. Yeah, so I'm not showing it here, but you can read the paper if you're interested. This dt of k diffuses according to a diffusion equation that you can write down easily, but you have to get familiar with these kinds of derivatives. So what shouldn't be surprising here is, oh yeah, the isotropic measurement had a Casimir operator. So this sort of like is a jx squared plus jy squared plus jz squared kind of differential operator. I'm hoping that you'll be comfortable enough with accepting that. But here, what's important is because we have a group structure, you can infinitesimally displace according to that instead of changing a parameter a little bit. Okay, so these are not coordinate derivatives. These are so-called right invariant derivatives. Okay. And something you should notice immediately is, well, this is a three-dimensional diffusion. And we're talking about this six-dimensional manifold. So what's going on there? Well, in that case, it's important to acknowledge this kind of Laplacian is actually what I would call a non-integrable or non-involutive Laplacian. What that means is that you're not actually going to stay in 3 dimensions. You're actually going to diffuse in all 6 dimensions, even if you're taking steps in only 3 dimensions at a time. And that's just a simple reflection of this fact that, you know, when you look at these commutation relations, so these derivatives have commutators basically the same up to a minus sign as the commutators of the operators. But if in this context, the fact that Hermitian operators commute to anti-Hermitian ones actually means that these sort of other 3 dimensions, so these are Hermitian displacements, if you will. There are other directions that you'll step into second order. So maybe a group way of saying that is, well, the product of 2 positive operators isn't positive, but rather it's positive times a unitary. Okay, so all of these are just different ways of appreciating that this Laplacian, though it is locally 3-dimensional, actually explores the entire space SL2C. Okay. Okay, so great. There is the Laplacian. But now what I'm going to do is process it in a way that might look a little more approachable. So the Cartan decomposition was originally invented to talk about precisely these kinds of manifolds. So in this case, you might recognize that the Cartan decomposition, well, I should just say, the Cartan decomposition is equivalent to the singular value decomposition. So this is, you know, any operator can be written as a unitary, a positive diagonal, and another unitary. But it's really important to emphasize that you can use this factorization property without ever caring about what the eigenvalues of this e to the jza are. Okay, so a Cartan decomposition is the same thing as a singular value decomposition, but the point is not to get singular values. In fact, this has different singular values depending on which j you use. But all of these results are independent of the j you consider. Okay, but in that case, these terms you might be familiar with mean things as far as the measurement is progressing. So this unitary on the right is just the direction of the POVM, right? K dagger K is the POVM element, so this V gets annihilated. So this U is the direction of the outcome. And then this A is basically how big the Q function is. So when A is infinite, then you have got a minimum uncertainty Q function. And we'll go over that a little more. But then this U is the direction where the thing is pointing, where K dagger K is pointing in the phase space correspondence. Yeah. Okay. So that being said, I'm just going to state here that if you can use this Cartan decomposition to do a transformation between the derivatives, those right invariant derivatives of the last slide, to more approachable coordinate derivatives and covariant derivatives. Okay, so all I'm saying here is you can use the Cartan decomposition to get a different expression for your Laplacian. Okay, it's still three-dimensional, yeah, but it's sort of aligned to the problem a little better. Okay, all of that being said, SL2C is six-dimensional. Thinking about moving in a six-dimensional manifold is intimidating. So now I'm going to quickly move to an analogous problem, which I think will illustrate a lot of the features of what dt of k is doing. Yeah, Carl,
Chris,
did you have something? Yeah,
I hate to interrupt again.
you should.
I told Chris this morning, if you could go back to the previous slide,
Oops.
Chris was talking about this, and I told him, Chris, you have to say the blood, sweat, and tears that finally got the Cartan expression for the IML, because you know that when you showed me the isotropic measurement Laplacian, that was not called that at the time. Well, I'm a theoretical physicist, and I said, Chris, this is the most beautiful thing I've ever seen in my life. But then it was a year to transform that very beautiful thing into this expression for the Cartan expression, which you can actually look at and see what's going on. And that was the blood, sweat, and tears.
Yes, it was very, very bloody indeed. Yeah. Yeah, so I think just to point out to you guys what that was about. So, you know, I showed this expression for the Cartan, the isotropic measurement Laplacian to Carl at the beginning when he started paying attention to it. And to establish that the continuous measurement does the spin-coherent measurement, I didn't actually need the Cartan expression. But Carl, realizing that you should be able to just see the whole thing if you just work it out, very stubbornly pushed us in the direction of manifesting this Cartan expression for the isotropic measurement Laplacian. Yeah. Yeah. Cool. And because of that hard work, now we actually have the ability to visualize what's going on. So here, I'm going to do my best to illustrate to you guys the analogous problem of diffusing in SL2R. Okay, so SL2R is three-dimensional. It's generated by sigma x, which is real, sigma z, which is real, and I sigma y, which is real. Okay. So in this little red box, I don't know if you guys noticed, but this little red box is piling up what we've been talking about. Okay, so there's a semi-simple unraveling with the cross operator distribution, isotropic measurement Laplacian. But now that we've moved to SL2R, these unitaries on the left and right have just turned into y rotations. Okay, so if you thought about rebits and stuff like that, maybe you can think we're restricting to a rebit, but there doesn't actually exist an isotropic measurement which does this. We're just doing this for visualization. Okay, in which case, yeah, you get the same kind of Laplacian we did before, except you only get one of these novel y's. And this is what novel y is explicitly in terms of coordinate changes in this left and right unitary. Okay, so here is a cylinder illustrating SL2R and its geometry. Okay, so I have an Escher here to emphasize that this cylinder I'm drawing, the sort of biggest cylinder you could draw here is a cylinder out at infinity. Okay. So this Escher is just to illustrate that in these two directions, you have a hyperbolic space. Okay. While in the vertical direction, you actually have a circle. So here we have periodic boundary conditions, okay? So if I start at the identity and I start rotating in the y direction, so if I leave a equals 0 and phi say equal to 0, then I dial psi, that would take me up until I eventually got to the 2 by 2 matrix -1. And then it would keep going until eventually at 4 pi, I would end up back at the identity.
Chris, I don't see a pointer. I don't know if everyone else does.
Oh, okay. Yeah. So
Are you pointing to certain? I think you're tracing out something on this.
oh,
diagram, right?
yes, I am. And you don't see the pointer. I see.
Is that just me?
Okay.
No, I don't see the pointer either.
Okay.
Oh, thank you. That is a valuable piece of information. So let's see. What can I do here? What did that do? Did that do anything? Oh God, I don't know what that did. You can. I just hit the spotlight button and I have no idea what it did, but it changed the.
It advanced the slide, I think, but we still don't see a pointer.
How do you make the pointer visible? Oh my.
Are you using Keynote?
I am.
Does anything pop up when you right click on the slide?
Probably have to temporarily get out of presentation mode because I think it just hides your cursor.
Okay.
I think
Yeah,
there's,
I
if you
think
go into Keynote, Keynote preferences, and there's a button you hit that says show the pointer.
Okay, so it's not a Zoom thing, it's a Keynote thing, perhaps. Slideshow?
Yeah, we can actually see you now. You're not in the demonstrator mode. We can see your pointer.
Why don't you just
Okay, show pointer. Thank you, Mike. I found it. So I'll do that. Try to resume. Can you guys see the pointer now?
Yep.
Great.
Thanks, Chris.
Cool. Yeah, thank you, Mohan. Okay, so yeah, so what I was saying is this cylinder is hyperbolic in these two directions, while it's actually a circle in this direction. Okay, so this is a periodic boundary condition. I should have written, but this figure sort of got over too much too quickly. But in this vertical direction is the one parameter subgroup of y rotations. Right? So if I were to rotate in the y direction, I'd go all the way up. And eventually when I rotate by 4 pi, I would end up back here. Okay. All right, and then there's two more one parameter subgroups, which are the getting measurement outcomes only in the z direction and getting measurement outcomes only in the x direction. Never going to happen, but you could still imagine the group. And now what is the next thing I have? Okay, so this cylinder I have here is for a fixed value of a. Okay, and what I've done is I've cut it down the side and unfurled it. Okay, so in this case, these red and blue lines correspond to changing either the left or right unitary. So I need to move you guys real quick, excuse me. Okay, so so this red line, for example, is changing psi. So it actually goes at a slant. I think one way to see that they go at a slant is if you dialed psi as minus phi, that would be the same thing as conjugating, and conjugating would take you straight to the right. But if you only do a one-sided rotation, you actually have this tilted motion. Okay. So for example, this everything in one red line has different values of psi, which means that they are cross operators that correspond to the same POVM element. And similarly, if you were measuring the identities, the mixed maximum and mixed state, cross operators that were on the blue line would give you the same post-measurement state. Yeah. So yeah, you get these funny spirals. If you've ever looked at hop vibrations, they're basically, so, you know, the SU2 has a Cartan decomposition too, except there's an I in the middle. And you can use that to visualize SU2. So this is like a hop vibration, except it's for SL2R, not SU2. So I guess maybe put another way, this cylinder is actually a torus, right? It's periodic conditions on the top and periodic conditions on the left and right. Another way to see that this is a torus is because multiplying on the left by a rotation and multiplying on the right by a rotation are operations that commute. It doesn't matter if you do that left one first and then the right one. So that's the same thing as saying that they have the same shape as two circles, i.e. a torus, product of two circles. Yeah, and now the angles of these, so these are called fibers, and in particular, I'm going to call the red ones the post-measurement fibers. Yeah, so the angles of these fibers are actually very important. So this is actually a kind of Minkowski space with periodic conditions on the sides. And this gray X is actually what lifelike vectors look like, things that are zero under the, I haven't talked to you guys at all about the Minkowski metric behind everything. There is one. So these nobler Y's, oh, here, I think I have another helpful thing to write. Okay, here's a pinwheel. So as you can see in this isotropic measurement Laplacian, there's two kinds of directions you'll step in. You'll step in the DDA direction sometimes, and you'll step in the nobler Y direction sometimes. Okay, so this pinwheel is supposed to illustrate that there are these two-dimensional planes that wherever you are, there are two directions you might take a random step in, but not the third one, not to first order. And so the way these are arranged at the identity, of course, you're stepping in Hermitian directions. Those are those weak LXs from the beginning. But as you step away from the identity, these things start to tilt, right? So here's the, you guys are looking at me, I'm gesturing some stuff. Plane in the middle, then these other planes that are starting to tilt. Yeah. And yeah, the non-integrability just has to do with the fact that these guys are tilting like this. There's a twist to these planes. Yeah. Okay, so this picture is to illustrate different values of A equals 0, A smaller than this picture, and A equal infinity, where at A equals infinity, these fibers are actually light-like. Yeah. And something Carl really likes about A equals infinity is you can see that nobler Y, if you're at infinity, nobler Y points along the post-measurement fiber. So what that actually means is that the measurement does stop because all it keeps doing after some time is change the post-measurement state. It just drives you up and down this red line and does nothing to the blue line. Doesn't change you along the blue line. Yeah, so, okay, so all of this being said, there's this two-dimensional diffusion going on. So before you start the measurement, right, your POVM is just a delta function. You're doing the identity measurement. But then your cross operators start to diffuse away from the identity. And they diffuse according to these two-dimensional planes. But because these two-dimensional planes are non-integrable, they actually diffuse basically everywhere. They just sort of do these spirally kinds of diffusions. So they don't go perpendicular to this plane yet. They have to go around before they go in this direction. But all in all, if you're diffusing in this kind of space, there's only one place to go, which is to the cylinder infinitely large. Right, so for all of the positions that are in the core of this space, eventually they will have a measure 0, because all of your measure is going out to infinity. Okay, so what this is supposed to show is it's apparent that your cross operators end up on the edge. Okay, so Oh, I guess in that case, yeah, here on the this flat hyperbolic space of positive operators, the edges correspond to rebit states. But remember, this applies to any representation. So points on the edge in that representation will correspond to highest weight states, if that means anything to you. Yeah, and as I was saying, if you go down a red fiber, for example, so yeah, let's do that one. If we go down the JZA direction, say we just happen to get a whole bunch of measurement records, right, that eventually landed us here, because they're going to land you somewhere far out. Actually, sorry, Carl had a nice little squiggle. So this is Carl's squiggle of a random event ending up on the boundary. If you got a measurement result that landed you here, then the outcome of that measurement would be the spin coherent state in this direction, the plus X direction. Yeah, and if it was anywhere else along this red line, then it would be the same n hat, but a different m hat. Yeah, sorry, that was a little awkward on my part. So do you guys have any questions? Do you feel like you have any sense of this diffusion I'm talking about? This funny 2D diffusion that gets you everywhere on the edge. Do you buy it? I disagree with it.
Yeah, so I was just going to ask, I mean, so yeah, what you're saying is that basically what you expect this distribution to do is it starts, if I started the identity, it's a blob that sort of grows out, and ultimately it's kind of a ring in this plane, like you're far towards this edge at long times.
Yeah, it doesn't go in the Y direction yet. It just first starts going out, straight out. Yeah.
And then thinking about a single trajectory at long times, the POVM direction is fixed, but the post-measurement state thing will continue to wiggle any old way.
Yeah, and that's reflected by the fact that the post-measurement fiber, these red guys are Minkowski orthogonal to nabla Y. And a great feature of if you boost the crap out of two things that are Minkowski orthogonal, right, you get this funny behavior that it then only drives motion up and down the fiber. Yeah.
Oh yeah, and nabla Y, sorry, yeah, that's right. So because we're in this real case, there's only one of these nabla direction. Yeah, so like this A direction is, the measurement is progressing, and then the Y, okay. And so in the real case, that'll be in the real case. In the SL2C case, that's basically two different angles of post-measurement state.
Yeah, cool. Yeah, and so then to continue on that, so because you're diffusing in the A direction, and because of these sinh squared A terms, you actually diffuse in the A direction very quickly. And yeah, so that's part of what makes this measurement efficient, is you get blasted onto the boundary. So the A part of the diffusion, yeah, is very quick. But the fact that the space is not compact, right, then the argument is the same. If you diffuse in a plane, right, you're going to end up all the way out there with high probability. So the same thing's happening here, but there's actually this accelerated effect because of the hyperbolic nature. Yeah. Yeah, and then the rest of it is just what is nabla Y doing? Yeah. Yeah, cool. Are there any other questions or comments?
Chris, I have a question about the original statement of the POVM, right? Is there a way to think of that as a diffusion on a sphere? Right? Because there you're evolving by generators of rotation by different DWs. That seems like a diffusion on a sphere too, but I guess you can't have the nice analysis of that.
So are you asking the question? So here I'm talking about the distribution of Krauss operators. you can ask the question, what is the distribution of POVM elements? That's easier to visualize. And indeed, that's in the paper. So in this case, the POVM elements, remember, POVM elements are just equating everything on the red line as one point. So actually, the Escher is the space of POVM elements. Okay. Okay. So in that case, yeah, everything is the same, but there's no discrepancy in what this M hat is. There's just the question, what is N hat? And yeah, in a sense, you can say then that the block sphere is actually the edge of this Escher, right? And it's filled in hyperbolically, right? The cross operators or the POVM elements just fill in the block sphere in a representation independent way. So it's not exactly a block sphere, right? It's the face of the spin J system. Yeah, so because we're just talking about SL2R, then we're talking about a block circle. Yeah, all of the same things carry over in SL2C. Yeah, so it is not hard to look at the distribution of POVM elements. It is a simple integration over the post-measurement unitary. Yeah.
Chris,
Yeah.
could I make a little comment on that?
Please.
That is absolutely true that you can write down equations for the marginal over the fiber, that is the post-measurement unitaries, and get a density for the POVM elements. But it is important to remember that the Krauss operators pile up just by multiplying them up. So you can write down an equation for how they evolve, but POVM elements don't do that. You can't just go from the POVM element now by multiplying by the next POVM element. You must go back to the Krauss operators. And that is why the only way you can get a distribution for the POVM elements is to marginalize over the Krauss operators, that is over the post-measurement unitary. You can't get there by just kind of starting with that. Or to put it more directly, you can't write down a stochastic differential equation for the pieces of the POVM element without including the piece that's the Krauss operator, because they're coupled. So that's an important thing to think about. Another thing, Chris, of course, knows that I love metrics more than he does. And when you guys hear that Minkowski orthogonal, Jesus Christ, you should be, where does that come from? That is literally here. The fiber has the opposite signature metric, opposite signature from the positive operators. And this literally is a problem with a light cone and a Minkowski style metric. In SL2C, there are 3 time-like dimensions and 3 space-like dimensions, and that's what this is about. And it is just so wonderful that you can understand these directions of diffusion by saying that the direction of diffusion is Minkowski orthogonal to the fiber. And finally, I think Justin made a comment and he didn't want to interrupt you. He was too polite to interrupt you, so maybe he should do that now.
Sure. Yeah, the comment I meant is actually closely related to what you just said about this Lorentz structure, this light cone structure. And it was just a side note that when you have a spin system, because it's angular momentum, which is generating angular rotations, that is naturally a subspace of the Lorentz group. And it turns out when you look at the generators for rotations, they only differ from the generators for boosts by a factor of I. And so there's naturally a 6-dimensional Lorentz structure whenever you're talking about angular momentum in this way. And if you think about this in a Lorentz invariant way, just think about a particle spin, how you're going to look at an interaction with that spin in multiple reference frames. Then if I induce a rotation of that spin with a magnetic field in one frame, and then go to a different reference frame, then that magnetic field will partially morph into an electric field, which will then have a spin polarizing effect in that frame. And that spin polarizing effect is that measurement effect. And so just by going between different reference frames, you're converting what is unitary in one frame to an actual measurement in another frame. And the quantum formalism, that's distinguished by this unitarity versus positivity that you're writing down. So it's actually necessary when you're dealing with relativistic systems that you have this full structure there, at least for particle spin. But it's a very interesting correspondence.
Yeah, so Justin, when you were talking about all that, so, I appreciate that SL2C is accidentally the same thing as the 3+1 dimensional Lorentz group. And when you started making the analogies between electromagnetism and measurement, I couldn't tell how much, do you have more in mind than just the accident? Like, are you actually thinking about measuring electromagnetic fields?
Yeah, so if you think about an actual particle that has a point spin, point magnetic moment, if I'm going to measure that magnetic moment somehow, practically in the lab, I have to put that particle through some device. That device is going to have some electromagnetic interaction with that particle point spin. Now, what that looks like when I write it down mathematically will depend on which reference frame I write it down in. And so if I think about just say a Stern-Gerlach apparatus, one of the simplest, like prototypical qubit measurements, right? The electron goes through and it bifurcates into one of two outcomes, and that's your projective measurement, right? That's done by going through this magnetic field. Well, how I describe that will depend on which reference frame I'm describing it in. And you'll see that there will be different contributions from magnetic versus electric components, and those will correspond to these different group generators in different frames. And so as you boost between different reference frames to describe it in, then what you'll see is that these Lorentz generators will sort of rotate into each other in the 6-dimensional space. So it's actually really important that this whole 6-dimensional space is there for the case of point particle that has spin. Now, the fact that this is also true for any qubit, no matter what it is, I think that's a curious thing because it doesn't overtly seem like it should be related. But it is necessarily there for relativistic point particles and spin measurements.
Gosh, sounds like there's a lot to talk about there.
Actually, since I'm interrupting anyway, I have one question on this slide, Chris.
Yeah.
Just to make sure I'm understanding kind of conceptually. I like to think geometrically when I can. And so my vision of your cross operators is as a map between like an input manifold and an output manifold.
Okay.
And a measurement map is typically contractive. So I can think of, let's start with an input manifold, and then I can take any input state on that input manifold, pass it through this map, and I'm going to get some output submanifold of that, which is typically smaller because it's a contractive map. Now, if I compose a bunch of them, then I'm composing contractive maps. And so what that's going to do is give me a net output space that'll be some subspace of my original manifold. So I think the question you're asking at the beginning is, what is the final subspace in the output space after composing essentially an infinite number of these things?
Okay, yeah, I think
stable like fixed point manifold. Is that
right? Yeah, so I think you're asking exactly the opposite question Mohan put. So yeah, once you have the distribution of Krauss operators, yes, you have the distribution of POVM elements, but you also have the distribution of post-measurement states. And it has this contractive property, you say. All post-measurement states quickly become spin-coherent states, right? And so those two, and something I was pointing out here with this MBRA and KET is that those are actually very different directions in general, that the post-measurement state is not the outcome of the POVM. But yeah, the sort of, I guess you could say then, given a distribution, God, I don't know how to think of dt of k as a map, but it has these contractive properties. And to each k, right, there is this flow, takes your manifold of rows. But then to think about sampling all of those different paths given your distribution, so integrating over k, then yeah, you'd have to, yeah, I guess you would just, to calculate the final distribution, you'd integrate against this dt of k.
I guess where I was getting a little lost was the distinction between the output manifold, which I can see is contractive and you get a fixed point, and this input space, and why the input
Which is
space
equally
never
contractive.
changed.
Why it never changes?
Right, because if I take an input space and then I compose a bunch of contractive maps after it, all I'm doing is changing the output space. So
Right.
I'm not seeing why the input space is actually that relevant other than just picking which states you're going to pass through in the first place.
Oh, yeah, I'd say the input state is not relevant.
So it is then maybe sufficient to only look at the distribution of your M hat there, because you only care about the output, net output contraction.
Yeah. Exactly. So the distribution of, so I wish I could say this better, but the distribution of post-measurement states can be expressed as the distribution of input states and this dt of k. And once you see that, then you see that, well, if dt of k is 0 in a lot of places, it doesn't really matter what d of rho input is, right? And I think that's the best answer I can give, that yes, all the post-measurement states are basically independent of the input states,
Right.
as seen by dt of k. Yeah.
Right. Okay. Then I think I'm following. So thanks.
Right on. Oh, cool. Are there any other questions or comments?
Well, I might just comment briefly. I think one has to get out of the mindset of input states and output states. The intuition here is all about how this Krauss operator changes as you pile up more of them in this continuous way. And for a long time, everybody, including Chris's previous collaborators, would try to gain intuition about what these results meant by thinking about what happens when you have an input state and what it's doing. And that just doesn't get you anywhere. You must think in the way that Chris is now asking you to think in terms of this manifold. And I will point out another thing, though. The positive operators here are thermal states for a magnetic field in a certain direction. At the origin, you have the identity. That means you have infinite temperature. And as you go out to A equal infinity, you get to the pure spin coherent states, and that is you have zero temperature, and so your state is the things at infinity on these circles are states that are ground states of a spin in a magnetic field in a certain direction, and those ground states are, of course, the states of highest weight. So there is a way to think of this transiting this manifold in terms of states, but the way one is being asked to think about it is in terms of those as processes. They are Krauss operators and they are processes. I'll make one final little comment motivated by Justin's comments about the Lorentz group. The statement that Chris made about the product of two positive operators is not a positive. That is, there's a rotation connected with it. That is identical to the statement that the product of two boosts in different directions generates a rotation. That is not just a similar thing. That is an identical statement.
Cool. Justin, I saw you looked like you wanted to chime in for a moment. Did you?
Oh, no, I was just agreeing. It's well stated.
Yeah, hooray, Lorentz group. Yeah. Okay, are there any other questions or comments? Okay, what time is it? Oh my goodness, yeah. So let's see. I think that is the punchline of the paper. So I think at that point, we have accomplished the purpose of the talk. Let's see, what do I have next? Okay, so this is, so I guess maybe I should just say, if you guys were thinking this is a 2-hour thing, you're welcome to leave. But I think maybe I'll keep talking. Yeah, okay, just a little bit. So I've got one more slide and then conclusion. Yeah, so this, I wanted to point out that this result, that the isotropic measurement of spin component performs the spin coherent state POVM, is actually equivalent to a fundamental theorem that algebraic topologists use. It's called the Borel fixed point theorem. So I want to state it to you guys, yeah, and then reflect on that a little bit. So in the Borel fixed point theorem, the setting is you have an irreducible representation of SL2C, in general a complex semi-simple Lie group, so like our Krauss operators, and you imagine choosing or fixing the irrep, okay, the quantum number J. Okay, so what we're thinking about are these so-called orbits. So given any pure state, of course, there is the space of all states that are of this form. So for most states, this is going to be some 6-dimensional submanifold of the Hilbert space. Okay, and these are going to have a shape to them. The Borel fixed point theorem says the following, which is that all of those orbits, only one of them is closed, and that is the orbit of highest weight. And so, yeah, what that means, right? Closed means it has all of its accumulation points. So if all of the other orbits are not closed, basically they have nowhere to go except to something that is closed. So yeah, it's fair to say that this theorem is equivalent, but of course it's not phrased in a differential geometric way. Yeah, and it's probably not obvious at this level that it's equivalent to everything in the red box, but it is. Yeah. Yeah, so that's worth mentioning. People who are really into groups and coherent states might appreciate this somehow in their own way. It's hard to tell. Yeah, and maybe the last thing I'll say, actually there's 2 more interesting things I want to say. I think you guys will really like this. So, so the thing to point out here is we never really talked about collapse time, but it does take a finite amount of time to go from being able to simultaneously measure to finishing the POVM. And of course, it takes a finite time because there is no sort of Arthurs-Kelly version of this measurement. And yeah, so I don't know how to say this better. This is sort of a conjecture for now, but it becomes apparent to me because of these results that, you know, this finite collapse time exists precisely because the phase space is curved, i.e., so curvature in this setting is the same thing as what do double commutators do. And double commutators in the standard coherent state setting are 0. And so the phase space is flat, but the 2-sphere is not flat, corresponding to the double commutators not going away. Yeah, I have a picture of Penrose here because I know that he thinks about at least gravitation and collapse times. I sort of imagine that he might be thinking about these things too. I don't know if he thinks about Krauss operators, but yeah, so this is an interesting question to me, the relationship between curvature and collapse time. So curved measurements in a sense have to have a collapse time. That's my interpretation of part of this result. Yeah.
So I can jump in there, Chris. That reminds me of those experiments a few years ago where people measured sort of time resolved the collapse of a superconducting qubit, and Howard Carmichael played a big role in the theory of that. If you're familiar with that, can you comment on the relationship there?
No, I'm not familiar with that. So let me just try to repeat back to you what I think you said. So Howard Carmichael thought about superconductivity related to curvature and
No, these are superconducting qubits
oh, okay. So he was thinking about
at
qubits.
transmons, and there was an experiment that was able to time resolve the quantum collapse, the collapse in a measurement. And actually, I remember Howard gave a talk at Squint a few years ago. So other people here might understand it better than I do.
Is this related to, so when I think of collapse times being directly measured, I think of, oh gosh, think of another guy on the East Coast. Quantum jumps guy. Carl, what was that guy's name? He visited UNM while I was there. I just want to know if he's related to Carmichael at all.
Michelle Deveray gave our
Yeah.
while you were there, and you know, it was really Howard Carmichael who formulated all the theory that both guided the experimental design and also justified the conclusions that they drew from what they observed. And it's an extremely interesting experiment because they are basically what's, you know, if you look closely at it, what's driving the apparent Rabi oscillations is the measurement, not the underlying dynamics. And so what they're able to do is show with a measurement that when the atom, which is going between some shelving state and some state where it's oscillating, when it does this change, it does it continuously, at least in this, or semi-continuously, and they can track that by making measurements that show that the thing goes around the Bloch sphere like this instead of going through the center. I'm not going to be more specific than that. It's a very interesting experiment. I think it's one of the most interesting experiments that has been done in recent years, and especially given the very careful theory that Howard did to interpret it. I'm not sure it has anything to do with this curvature and collapse times, and to be sure either one way or another would require this seminar to go on for several more weeks.
Yeah, so cool. So thank you for answering that. I know Justin's thought a lot about quantum jumps, and I've never thought of, does this, I'm sorry, I don't know the connections between you and Carmichael Deveray, if they are. I don't know. So big, I don't know.
So yeah, Andrew Jordan and I are part of a team working with Irfan Siddiqui, who also does superconducting qubit experiments.
Okay.
We've done a lot of continuous measurement type work with him. This particular experiment by, I think, was Zlatko Minev, who did the experimental work with catching the quantum jump, if I'm looking at the right paper there, is extremely interesting. But with respect to this collapse time, this is often limited essentially by the information flow between the qubit and whatever's detecting the qubit. So in this case, there's a qubit and there's a superconducting resonator that's coupled to it. And that superconducting resonator has a line width, which then leaks to a transmission line, which is then amplified and measured. And so the line width of that resonator actually dictates kind of the time scale over which both the qubit information is being averaged by the resonator and the time scale over the response of you detecting the signal. So this collapse time is closely related to all of these various coupling timescales involved in that readout chain. So it's not just the geometry you're talking about here. Probably this gives a kind of lower bound or something like that.
Right. Yeah.
I had a few comments if you're at the end of your talk, Chris.
Andrew.
Yes, so first of all, very nice work. I was really interested in the geometric aspects and the algebraic aspects. It really takes the whole theory to a new level, which I appreciated quite a bit. I've been interested in this question of non-commuting measurements for a long time, and so I'm interested that you're making progress on it. So I have a paper in 2005 about measuring sigma x and sigma z at the same time.
Okay, okay.
And then there's a paper in 2010 by Korotkov, Ruskov, and Molmer that does exactly this problem of sigma x, sigma y, sigma z.
Okay.
You're able to solve it exactly in this isotropic limit that you're interested in. And so if you're not familiar with that work, I can give you the reference, but it's very closely related to what you're talking about. And then furthermore, there's actually been an experiment by the Siddiqui group where they jointly measure two of these observables at the same time, sigma x and sigma z. And so this experiment has been done. And so we have a further follow-up theory paper looking at correlations amongst these observables, both experimentally and theoretically. So I was interested to see also you were thinking along the lines of the path integral approach to this composing the Krauss operators. This is something very much that we have a whole series of papers with Justin and collaborators about this path integral approach to continuous measurement. So that's very much along the lines that we've been working over a number of years. So I was interested to see those connections with your talk as well.
Yeah, wow, it's a whole other world. Okay, so will you, if I contact you, you'll help me remember these references you just.
I'll send you an email and to you and Carl tonight, and I'll give you some references about those works, and you might be interested to look at them.
I will. Thank you. All right. Thank you so much. Yeah. Okay. So there's one more slide I'd like. Oh yeah.
I just have a
Moha,
general
yeah.
question. So maybe I'll wait till your last slide.
Okay. So we have one more slide. I promise. So this entire result applies to any complex semi-simple Lie group. And you know, if I have sort of half a paper written on that fact, but of course, Carl wants to be able to see the whole thing. The algebra isn't enough. And I wanted to just bring this example to your guys' attention. So, you know, the BCS coherent states are superconducting coherent states, and you can think of them as an overcomplete basis for at least even parity fermion states, which means that if you isotropically measure these quadratic observables in the exact same way in exponential time, you do this tomographically complete measurement, whose outcomes are the superconducting states, BCS superconducting states. So, you know, this was interesting to me because here you have a fermionic phase space correspondence where you can measure Q functions, etc. But of course, the fair analogy to bosons is to imagine using this funny phase space. So there's this funny thing here that I'm using as displacement operators quadratic stuff. Yeah, so I thought this was interesting, that you can effectively do this measurement if only you knew how to measure all of these observables continuously. And so I have this little comment that, well, I guess number preserving stuff is current and voltage measurements. I have no idea what this CC kind of observable is. I have no idea. So I wrote what the von Neumann, because I don't know.
Chris, I can comment there. This is closely related to amplifiers and this kind of hyperbolic space that's generated by this double dagger kind of observable. That's been featured in another Siddiqui experiment where they used squeezing to enhance measurement fidelity and all that. So you might look into that. It's closely related to this question of transformation and squeeze.
Yeah, and in the fermion case, you know, because you know, these are like amplification, except if you amplify enough, you actually get back to the vacuum. And so, yeah. Did you say you had a reference to recommend?
Yeah, I can join Andrew in sending you some fun reading.
Yes, please. Thank you. Yeah. So all of this being said, Yeah, I thought it was interesting to realize you've got this measurement that creates random superconducting states. And, you know, I don't know a lot of solid state physics, but at least 10 years ago, there's this big question of what mechanism allows for high temperature superconductivity. And so if it turns out that like the environment of the superconductor is doing these kind of measurements, I believe that means this is a mechanism for high temperature superconductivity, but I don't know what I'm talking about. Yeah. Yeah, so that was interesting. I just wanted to share that with you guys. So yeah, acknowledgements. Thank you, Carl. Thank you. Mohan is my current boss at Sandia. He's been very patient to let me finish this work. And yeah, we've been having some great conversations about quanta in the shapes of manifolds, because he's been thinking about that for a couple years. And yeah, Carl's been working with me very closely on this paper. Yeah, what we've been talking about is, I think the isotropic measurement is very fundamental. It shows that there's a relationship between continuous measurement and coherent measurement, a very specific kind of relationship. And then I pointed out to you guys at the very end, it makes me think about questions of the relationship between curvature of a phase space and collapse times and other phase space correspondences for fermionic systems, etc. Yeah, if you like my talks, here's a couple more that you might want to watch and check out the publication. Yeah. Okay, so that concludes the talk. Yeah.
Thank you very much, Chris, for a very nice talk.
Oh, thank you, thank you, thank you. Mohan, you had a general question? Or
yeah, I do. It's actually, I'm glad you you went to that extra slide because it's very related to that. Just so I understand that last bit, is the message there that for any semi-simple Lie group, if I measure all the generators isotropically, I collapse onto the generalized coherent state associated with that Lie group? So the algebraic coherent state?
Yeah, that's exactly right.
Okay.
Generalized coherent state being defined as in the orbit of highest weight. So like, you know, orbit of the vacuum for fermionic systems. Because, you know, a lot of people took away from Paralamov's work, generalized coherent states should be orbits of any state. But yeah, when I say generalized coherent, I mean highest weight. And that's part of the not so expensive, right? Yeah. And
have you looked at the relationship between the post measurement state and the so you said in the spin case there's this extra degree of freedom, right? That the post measurement state doesn't have to be the same as the outcome, unlike the harmonic oscillator case. Is that generally true? Is it just that the harmonic oscillator case is special, or
right, it's because of the way the Lie algebra is. Yeah, so for semi-simple Lie algebras, you always get this difference in the post-measurement state and the outcome. But you know what the post-measurement state is. So given the measurement record, you could apply a unitary that brings it back. And in fact, you can solve an analogous problem where you do live feedback to keep the post-measurement state in the same direction as the outcome. And you get this great non-abelian gauge theory, and you know, and yeah, so that's an interesting thing to think about. And yes, it's a general feature that you would have to actually drive the post-measurement state to stay in the direction of the outcome. And that's a reflection of the curvature. The fact that the second.
Right. Okay.
Yeah.
Thanks.
Yeah.
Okay. So I just want to say, if you send those references to Chris, could I get those too? And perhaps other participants here want to get those emails too.
Sure, Stephen, I will copy you and you can forward on anything else to interested parties.
Okay, yeah. All right. Well, thank you very much, Chris, once again.
Yeah, thank you, everybody.
So there are no more questions. And yeah, I guess people can find this recorded lecture online. I recorded it to the cloud. So I suppose with the same link, you can find the recording. And if not, let me know.
Okay.
Okay. Well, thanks. Thank you very much, everybody, for attending.
Right on. Wow. Until next time. Bye, guys.
Thank you. Thanks, Chris.
Okay,
Thanks for the nice talk.
Thank you. Thank you.
Thanks very much, Chris. And thanks for organizing, Stephen and Mike.
Sure.
Yep. See you later. Bye.
Okay, bye. Hey, Chris, I still had one question, which may be very dumb.
Okay.
So,
Okay.
so when you talk about the isotropic measurement, at the very end of the slide, you have picked the z direction, right? Is that
I'm
just
sorry.
the way we pick always the z direction? Completely, you've picked the z direction here.
Right, right.
Is that the usual completely arbitrary direction and we pick it z because we can? Or is that
Right.
direction related to the measurement record?
Yeah, no, so you're talking about the z direction in the decomposition.
Yeah, that one.
Yeah. So you could choose, so the only reason it's z is, yeah, you could choose any permission matrix to generate this middle one. And they're all unitarily conjugate to each other. So I guess you could say, yeah, if I did another decomposition where I put x in the middle, there would just be different values of these parameters.
Okay.
Yeah.
No, but it's that z direction that we always choose just because we can pick whatever we like. Okay.
Exactly. It is. It is.
Okay.
Yeah. Most of us think of z as diagonal, so it looked
Yeah.
like the best thing to put in the middle. Yeah. Yeah.
Okay. Very cool.
Phew.
All
Okay.
right. Well, nice to see you again.
Yeah. Good to see you.
And,
I think
so
we'll
good
talk
luck
again
tomorrow. You
soon.
give another talk.
Oh gosh, yes, I will.
Okay. Yeah.
That'll be much more fat, streamlined.
Yeah.
Okay.
Okay. Very good. Well, again,
Stephen,
good luck.
thank you.
Thanks very much.
Thank you. Thank you. Until next time.
Bye.
Bye. Bye, Carl. I'll talk to you later.
Great job. Thank you. I hope I wasn't too much of a nuisance.
Oh, you were wonderful.